It's a great pleasure to have Ricardo Baptista with us from CALTECH. And of course, Schneider and the short-based diffusion models. So he will be talking on dynamics and memorization behavior of short-based diffusion models. Ricardo, floor is yours.
Perfect. Thank you very much, Satiros, for the nice introduction, and to all the organizers and staff for putting together this extensive 4-week program. I'm excited to share some recent work on the dynamics and memorization behavior of these models. So this is something that, at least the memorization aspect, is something that's been highlighted over the last few weeks. And I hope to share a little bit of insights on how this occurs from a dynamical systems perspective. Before getting started, I just want to acknowledge my collaborators on this work. So this is joint work with Nikola Kovacsky, who's here in the back, and Andrew Stewart, both Nikola from NVIDIA, Andrew from CALTECH as well, and Agni Dasgupta and Asad Oberai from the University of Southern California. So together we're working on some work that studies the memorization of score-based diffusion models, and in particular how to regularize these models to avoid memorization. Today, I will just focus on the first aspect of that, just to understand the memorization behavior. But I'm happy to talk about regularization techniques offline for those that are interested. So to get started, I just wanted to remind and recall the overall task of generative modeling. So in generative modeling, what we typically have is a setting where we collect some IID samples, X not I. These could be, for instance, images, text, video, some collection of data that we presume comes from some underlying probability distribution P0. And our goal is to come up with a model that can generate samples from this distribution P0, but most importantly, samples that are not present in the underlying training data set. So some new, fresh samples. And over the last few years, we've seen examples of how different generative models can achieve this task. So in machine learning, we've seen lots of great examples of these prompt-to-image models from different companies that have shown how to generate presumably new images, like of a teddy bear riding a skateboard in Times Square. Presumably this image did not exist before, or of a temple in overlooked near a waterfall in India. And we've also seen a lot of applications throughout the physical sciences to generate new objects like different molecules in biology, or to simulate different flows in physics, and in particular, even applications to tasks like super resolution and other inverse problems. But despite these nice images that we've seen, we often take at faith that the random samples that come out of these models are really fresh, new samples from the underlying probability distribution. And at the same time, there has been some evidence that we are not really getting fresh samples. So in some work in 2023 by a few groups at some folks at both Google and at DeepMind, it was shown that we can input certain images into the training set to learn these models, and the generated images might be very close to one image that exists in the training set. And even if it's not just a very close overall image that's reproduced, in some work from the University of Maryland this year, it was also shown that you can often get images that are maybe not exactly one of the images in the training set that are generated, but that contain a lot of the same elements of the images that were in the data set. So we can, for instance, see examples where the generated images are essentially contain everything that was present in pieces of images in the training data set. So our goal in this work is to really understand why and shed some insight into how this can occur potentially with these models in a more rigorous way. So to do that, the talk today is going to be broken down into 5 parts. So we're going to first just review and the methodology for diffusions and we'll go over some of the notation that we'll use throughout the talk today. Next, I'll present our main result on how this memorization occurs. I'll discuss the analysis underlying that result, present some numerics that describe and illustrate this, some of the insights from our theoretical results, and then finally conclude. So first on the methodology. So just as a recap for to get us started for the day. So in diffusion models, what we typically set up are 2 processes, a forward process and a reverse process, where the forward process takes in some data and maps the data by adding typically some noise and some corruption to the data to essentially noise at some large time to hopefully get us to a point where the samples that we get at this final time are no longer contain any information about the underlying data. And after we define this forward process, we then define a reverse that follows the same law at every point in time of the forward process, and that can be used to map noise that's independent of the data back to the data distribution to hopefully generate some new images. And the key part of this is that to define this reverse process, we need the so-called score function for the marginal distribution at every point in time. So looking at the, we need in particular this gradient of the log of the density of this process. And what we'd like to do is to define such a reverse process that generates samples from the underlying distribution, given that we only start with an empirical set of samples from the distribution at time 0. So in order to do this, because of the fact that we don't have the analytic form of the data distribution, at least its density, then we have to learn the score function for the marginal distribution at time t that we can, due to the fact that we have this stochastic process, forward process, we can write as the typically some convolution of the data distribution with some conditional kernel that maps us from time 0 to time t. And the approach that's been quite popular over the last years to do this is an approach that was popularized in some work in 2010 that where we set up essentially a regression problem for the score function where we look at a loss between some score that we're trying to learn S, the gradient of the log density at time t, the expected L2 error of that integrated over time. And what Vincent showed is that we can rewrite this objective function that requires knowledge of the true score at every time t in order to evaluate this loss. We can rewrite it in terms of an expected L2 error between the score and the conditional score for the density at time t condition on the initial condition. This is something that is defined by the forward process and that we typically know in advance. And in particular that these two objectives are equal up to an additive constant. So, and this constant doesn't depend on the score function. So if this constant is finite, then these two problems have the same minimizer. And so we can minimize this problem, this new objective that we've defined to identify the score without knowledge of the underlying data density. And so in practice, what's done is that we have some samples from the data distribution P0, X not I, these IID samples, and we discretize one of these expectations with respect to the initial condition X naught. And we get an objective that, an empirical objective that sums over all of these data points and in particular contains this conditional score of that condition on each one of the data points in our empirical data distribution. And we minimize this loss in order to identify an estimator for the score. And then given that estimator for the score, we then simulate our reverse process, either the SDE or a corresponding ODE that has the same law in order to generate approximately new samples from the data. So just to give a concrete example of this that I'm going to use throughout the talk today, one common forward process is what's often called the variance exploding process. So this is the forward process where we just essentially add noise to the data. So we have the forward SD just defined without any drift, as dx is the square root of some diffusion coefficient times this Brownian motion increment dw. In this case, the conditional distributions for the distribution at any time t given the initial condition is a Gaussian centered at the initial condition x0 with variance sigma squared. That is the integral of this diffusion coefficient. And the score function is a linear term, x minus the initial condition divided by sigma squared. So we can use this score function and insert into our objective for denoising score matching, where we regress S against this conditional score evaluated at each of the data points and minimize this term to get our estimator, our optimal score function S star. And then to generate the new data, we'll then run a reverse time SDE that's given by this, that has a drift function, which is based on this optimal score S star times the diffusion coefficient squared plus some the noise term, or we can run this what's often called the probability flow ODE, or this reverse time ODE that has the same law, assuming that we started at the right initial condition. That is a deterministic sampler based where the drift is just based on the score function times the diffusion coefficient. And in practice, both of these processes are simulated by starting at some time capital T with a fresh sample that is independent of the data. In this case, with a sample that comes from a Gaussian with some variance sigma squared evaluated capital T. So with this framework,
sorry to interrupt. Can you go back? So one question for you. So now start the reversing time SD with a distribution that does not reflect the true distribution of the forward process.
correct.
And then the question is, it's also very difficult now to estimate what is the difference between this and your forward processing time.
Correct. Yes. Thank you, Satiros, for the question. So even making the equivalence between these two requires that these processes were initialized at the correct final time of the forward process. There is, and in practice, these are initialized at this approximate initial distribution and initial condition. So there is an error here. There is some work to understand exactly what is the offset in the drifts and how that can be controlled. And we saw a little bit about this work yesterday, as well as in the first week, and trying to control the error in the initial condition. But you're absolutely correct.
Sure, I'm saying that because I'm trying to see the benefits of this approach in comparison to the standard approach with Rost and Nuremberg. Where yes,
okay.
where there you can give some sort of an estimate of how far is your initial data for the backwards in time with respect to the forward. I'm sorry for the interruption.
No.
But
Yes.
just to hear from you, the advantages of it.
Of the variance. So in terms, I'm not going to comment, maybe talk today too much about the error in the initial condition, particularly for this process. But you are correct in that there is potentially more challenging to control versus the OU. But in practice, I would say part of the reason, the motivation is that it is popular, this particular variance exponent process. And with enough noise, you do still observe empirically that you don't see a lot of remnants in the data. Thank you. So this was just to recap the current procedure for performing score matching and then when these models are used in practice. But what I'd like to do next is to discuss in particular what exactly occurs when we have we just train one of these models with a finite set of data from a finite set of samples from the data distribution. And the starting point here is something that has been observed in a few different papers over the last 2 years, and in particular has also been highlighted in this workshop. So when the data distribution is just given by an empirical distribution of n samples centered at some points that for the rest of the talk, I'll just denote by x sub little I. What is known as that the optimal score function that minimizes the denoising score matching problem, the one that we introduced in the previous slide, is given by has a closed form expression, which is given by a sum of terms that are centered around each of the data points multiplied by some weights that I'll call Wi. These are weights which are normalized Gaussian weights. So we start out with some weights W tilde that measure how close X is to each one of the data points divided by the variance at any time t of the conditional variance of the forward process. And then these weights are normalized to be between to sum to 1. And the overall score function is given by the linear combination of these weights times these linear terms divided by this conditional variance. And this is essentially the score function for, as what's been described as just the Gaussian mixture for the distribution at time t that arises from integrating the conditional kernel that we get from the forward process against the data distribution. So the Gaussian mixture given by the sum of the Gaussians centered at each one of the data points with some variance sigma squared. And it's often been commented in various different works that this is essentially, because this is the optimal score function that minimizes the loss and the score contains all of the training data, then this will memorize all of the training data. And especially if we run this process backwards, we'll essentially just get back our training data. And so what we wanted to understand is exactly unpack that statement and really understand what is happening when we use this empirical score function. How does it actually get back to the training data? One thing I want to highlight is that these models are often used not just in an unconditional setting where we just want to generate data from some distribution P of x0, but also in a setting where we want to generate samples from a conditional distribution. So in the motivating slide, I mentioned some text to image models where we want to condition on some text and generate an image that is consistent with that prompt. And so that can be seen as trying to sample from some distribution of images conditioned on text. And that in practice is often done by setting up a similar forward process for the X variable, for the image variable, without adding any diffusion on the conditioning variable, and learning a score function that is not just dependent on X, but also on Y. But because of the fact that the diffusion is only acting in typically the X variable condition on the initial condition of the X0 of a sample of the image from the image distribution, then in practice, this denoising score matching problem in an empirical setting where we have samples of the pairs of images and prompts will actually have a similar minimizer that has the same form as what we saw in the unconditioned setting, which is given by a sum of linear combination of x's minus the training points at xi times some Gaussian weights. The main difference is that in the conditional setting, for any prompt or any particular value that we want to condition on, we can just think of, for instance, conditioning on categorical values like a cat or a dog. Then the samples that we would take in this sum are just the samples that are associated with one particular label. And so this score, using the score function, because it has a similar form, will have ultimately a similar behavior as what happens in the unconditioned setting. So we're going to focus on the unconditioned setting today, but a lot of the same intuition should carry over to this setting as well. So in order to kind of unpack what exactly happens with these empirical scores, I just want to first provide a little bit of visual interpretation of exactly what are these empirical score functions and how do they behave. How do they behave? So what we know is that these score functions are a linear combination of these linear functions times some weights, where as the input where these scores are evaluated approach any one of the data points, then these weights, let's say x approaches some data point xi, then the weight associated with the point I will become large. In particular, because all of the weights are normalized, it will approach 1. And the weights associated with all of the data points will similarly have to approach 0 so that the sum of them is 1. And this real divergence of the weights becomes particularly accentuated as the time t goes to 0. And that's because the weights not only measure the distance, but are also divided by this conditional variance, which is going to 0 as time goes to 0. So in this setting, as we're approaching any one of the data points, and time is going to 0, the score function is going to behave roughly as follows, where it's just the affine function x minus the data point xi divided by the conditional variance. And this is because all of the weights associated with all of the other points are going to 0. And so this is this is exactly the score function if we started at a Dirac at xi and just added Gaussian noise, and this would be the score function at any point in time t. In practice, what we have is not just one of these data points. So we have maybe a collection of data points like these red dots here on the slide. And at any time t, we have to account for this sum of all of these linear functions with some weights. And so we'll get something that's slightly smoother than these this what we have here. And that's displayed in blue in this plot. But as time goes to 0, what we're converging to is something that around each of the data points has this affine behavior. So something that looks more like the orange line in this plot is discontinuous at some points that we'll describe in a second. And moreover, that is actually becoming unbounded as time goes to 0 because of this denominator, this conditional variance, which is going to 0 as time goes to 0. What I want to focus on in this plot, though, is in particular the boundaries of these different regions that have this affine behavior. And to do that, one concept that's really important and that's useful for our study is what's known as a Voronoi tessellation of a collection of data. So if we have a collection of data points xi, then we can define what's known as a Voronoi cell, which is a collection of points x that are closer to xi in some distance. In particular, here we'll take the Euclidean distance, than the distance from x to all of the other data points. Here, of course, we're taking the Euclidean distance because the weights are defined based on the Euclidean distance, but one can also imagine working with a different distance function for the weights were defined differently. So for every point xi, we can define this collection of points x, this set. And if we take all of these cells, all of these sets for all of the data points, they form a partitioning of our domain where our data lives, in this case, typically RD. So going back to the picture that we had in the previous slide, these for every data point in red, we can look at what are the closest points to this data point that are closer than any other points. And they correspond to the sets that are divided at the midpoints between all of the data points. So in this dashed line, we have the boundaries of these different cells where we go from a point that is contained within the Voronoi cell, for instance, for this point at -1, to a point to the Voronoi cell for a point at 0 or -0.2. And moreover, these cells can either be compact for, in this case, for points on all of R, if they are within the interior, for instance, between 0 to 2, or they can be unbounded, for instance, for these boundary points. So we're going to work with this Voronoi tessellation throughout the talk today. In order to get to our main result, I just want to also describe exactly what is this reverse time system that we're going to consider now with this empirical score function. So for the variance exploding process that we introduced earlier, we're going to consider a case where the diffusion coefficient just scales linearly with time. The results can also be generalized to other diffusion coefficients, but we'll work with that for now. And if we, for this process, if we use the in form of the empirical score S star, the ODE that we get, this reverse time ODE, has the form given here on the slide, which is where the right-hand side of the ODE looks at the difference between the current position that we're at X and a linear combination of the data. So we'll denote that by this X sub n, the linear combination of all of the data points in our training set times these Gaussian weights. And all of this is divided by time, where this 1 over t comes from the conditional variance in the empirical score. And this ODE is really pulling our current point X towards this linear combination of the data. And this the pull is getting stronger as t goes to 0. In order to make the analysis slightly more amenable, we're going to work with a reparameterization of time. So we're going to introduce a slight change of variables. We're going to call s the negative log of t. This allows us to, instead of going from time, let's say 1 all the way back to time 0, we now get a process which we can integrate forwards in time. So time 1, the end point gets mapped to 0. And instead of mapping to 0, we now map to positive infinity. And we're going to evolve this new ODE in this new variable y. So dy ds is given by a right-hand side, which looks at the difference between y and a new term, which is also a linear combination of the data points with some weights. Where now the weights, the only difference is the time dependence of the weights gets evaluated based on this change of variables in S. And in particular, the objects that we're interested in looking at are the limit points of such an ODE. So we're going to look at, for any initial condition y0, we're going to look at limit points, which are the limit of when we take sequences of the value of the dynamics of the solution of this ODE as in time as this reparameterized time goes to infinity, and in particular ask whether these limit points exist and where they actually are contained. And what we show are two results. So the first one is that the limit points of this system y star are attained at one of 2 points. So either at one of the training points, this is something that we have discussed and that here we're going to show rigorously, but surprisingly can also be contained on the boundaries of these Voronoi cells. So of these, when you construct this tessellation, there are points on the boundaries which are limit points of these ODEs. And the second result is that when one of the limit points is one of the training points, so when y star is corresponds to xi for some point I, then the dynamics will actually converge to this limit point y star at this rate that's exponential in time, e to the minus s for these modified dynamics, and that where the rate is independent of the data distribution. So these two main results are what I want to unpack in the next section and show exactly how we arrive at and show this. So going into the section on the analysis of these of this main theorem. So in order to prove this, we show two important lemmas. The first is that the dynamics always live in compact sets. So from the ODE that we wrote down and using an integrating factor, we can write down the solution of the ODE and show that the norm of y at any point s is always bounded by the maximum norm of the initial condition and any one of the training data points. So because the dynamics live in this compact set defined by this term, then what we have is that we can look at sequences of the dynamics and extract converging subsequences and define our limit points to be the limits of those subsequences. And in particular, we have that the limit points then lie in some ball whose radius is given by the maximum norm of all of the training points. In practice, we can actually get a slightly smaller bald, but for the purposes of today, I'll just present this result. And then the second result, which is important, is that once we have this existence of limit points, what we also show is that the Voronoi cells associated with each one of the data points are invariant sets for the dynamics, meaning that once one of the dynamics enter within one of these Voronoi cells, after a sufficient amount of time, it will never leave that Voronoi cell. So mathematically, what we're saying is that if we consider Voronoi cell, which is just slightly within the Voronoi cell associated with any one of the data points, so separated from the boundary of the data point separated from the boundaries of the Voronoi cell by some distance delta, then we're going to call the subset of each Voronoi cell V delta for every data point xi. And if the dynamics at some point in time S star lie within this subset of the Voronoi cell, meaning that it doesn't touch the boundary. So the subset of the Voronoi cell V delta associated with the point xi, then for all, and this happens at some large enough time S star, then the dynamics will actually always lie within this Voronoi cell corresponding to the point xi for all time greater than S star. So I just want to show in particular why this result holds, because I think it's quite interesting, the analysis behind it. And really, it's where it comes from is a geometric picture. So if we look here on the right, what we have we can think of a Voronoi cell associated with every point xi as the cell given by the boundaries here denoted in red. Around it, we have other points that have their own Voronoi cells. And what we're going to consider is, let's say there's there's the dynamics at some point enter within this Voronoi cell in particular, just slightly within it so that they don't touch the boundary. And in order to show this invariance, what we need are three properties. So the first is that if we're near the boundary of this cell, in particular, let's say we're on this boundary given here, associated with the point xi and the neighboring point associated with xj, then if we have any, if the dynamics are along any point of this boundary, let's say y, then the vector y minus xi is a vector that's pointing from this point y to the interior xi. And this vector will always be, will never be orthogonal to the vector that defines the boundary of this plane, which is xi minus x squared. And in particular, and this is the reason why this holds is because really the boundary is a finite length. The second is that after a sufficient amount of time, once we are in this cell for any point in this cell y, the weight associated with the point xi is going to be approximately 1. And this becomes, as we mentioned earlier, more closer to 1 as time grows. And so this is where the condition on time is really important. And the weight associated with all the other data points is going to be close to 0. And so if we look at the difference between the nonlinear part of the right-hand side of the ODE and xi, this term can actually be bounded by after a sufficient amount of time by this the same factor that defines the minimum angle between the two vectors that we defined earlier over 2, let's say. And as a result, if we look at the inner product between the right-hand side of the ODE, dy ds, which defines in which direction the dynamics are moving, and the boundary, the vector defining the boundary for the hyperplane. This is given by the inner product of, because the dynamics look like minus y minus yn, we can always write that as minus y plus xi plus yn minus xi. And so we can look at that as being equal to the inner product of y minus xi, which is the vector that is given by where we are pointing towards the interior of the cell, which is always positive and greater than alpha. And a second term, which is going to be small because the weights are small. And so as a result, this inner product is always, can be bounded away from 0, and shows that the dynamics along the boundary always point inwards towards the center. And as a result, after a sufficient amount of time, we're always going to be pointing, if we get close to the boundary, we're going to be moving back towards the center of the cell and remain within the cell. And then finally, if we look at the ODE, again, we can also write down an ODE for the difference between the point y and the center of the cell xi. This is because xi is fixed. This is also equal to dy ds, and can be written in terms of the sum of two terms, one that's given by the difference between y and xi, and another term between the nonlinear part of the ODE and xi. And what we used, in fact, in the previous slide is that this nonlinear part of the ODE is actually very small because yn is close to xi. And so as a result, the dynamics are really just looking like dy minus xi ds is equal to minus y minus xi plus something that's very small. And so as a result, if we use an integrating factor and bound the difference between ys and xi, we can show that in fact this the contribution coming from this nonlinear term is decaying exponentially with e to the minus s. Similarly, the term from the initial condition, and the overall convergence rate is then also e to the minus s for the difference between the solution at y and xi. And this, as long as we are above some critical time, which we can quantify in terms of the amount of data and where the data is placed, we're going to get this convergence rate to one of the data points at a rate which is independent of the data distribution and the initial condition. That the contribution of those parts only enter into the constant. So in summary, what we have are that the model dynamics really have two parts, we can say. So one of them occurs before this critical time, where there is a lot of exploration of potentially of the data, and we can move anywhere in our space. But after some critical time, once you enter within whatever Voronoi cell the dynamics are currently, there's just going to be a collapse onto one of the data points if we're strictly contained within a Voronoi cell. So we also have this possibility that we will remain on the boundaries of these Voronoi cells, which is something that can potentially happen because our analysis doesn't rule that out. And moreover, when we do converge to one of the data points, we get this asymptotic behavior of the convergence rate, which is data independent and behaves like e to the minus s in these transformed dynamics, or behaves like t as t goes to 0 in the original time variable. So in the last few minutes, I just want to illustrate this through some numerics. And to do that, we are just going to look at some visual examples of what the dynamics look like relative to a collection of data points, random data points, and their corresponding Voronoi tessellation. So here what we plotted were 20 data points just from a standard Gaussian in 2D. These data points are in blue. The Voronoi tessellation associated with each of these data points is corresponds to these black lines surrounding all of the points. And then in red, we plotted the dynamics of these reverse time ODEs and starting from different initial conditions defined by the forward process. And what we observe is that these ODEs, the dynamics, for these initial times, they come toward the bulk of the data distribution. So for instance, looking at this first plot, they move from far outside the data distribution. So these plots are all zoomed into where the data points lie and move towards the data. And at the initial times, they can move across any one of these boundaries of these cells and move into different cells. But once this critical time is reached, then what occurs is that the dynamics tend to take a quick turn and move directly towards one of the data points. So what we observe is that, for instance, looking at this first plot, after some critical time, it's found that it's within this Voronoi cell that I'm highlighting. And at that stage, it just converges at this rate, this exponential rate in the transform dynamics towards the data point, which is right here, very close to that boundary. Similarly, for instance, this plot here at the bottom left, after that critical time, it will take a very sharp turn back towards the data point and converge to that point. But before that, one thing I want to highlight is that the dynamics do cross the boundaries and do explore potentially many cells before actually collapsing onto that point. Moreover, when we look numerically, we also observe this expected exponential rate towards one of the data points from the previous slide. One thing I want to highlight is that in those experiments with those random points, we always observe convergence to one of the data points. But there is still this possibility that one doesn't converge to one of the data points. And that can be seen in some setup examples. So for instance, if we take examples where we have 2 data points and we plot trajectories of the ODEs starting from different initial conditions on some regular grid around these 2 data points, most of the trajectories do converge toward these 2 points, but there are some trajectories that, if they're initialized on the vertical line x1 equal to 0, they will remain on that line for all time, because there's no on that line, the pull towards each of the 2 data points is the same, and so the only direction that one will move in is vertically along this line. So this line corresponds precisely to the boundary of the 2 Voronoi cells for these 2 data points. So there is this possibility that limit points will lie on this boundary. And this can also be seen in other examples. So for instance, if we take 4 data points initialized at various different initial conditions on some grid, then we again observe that most of the trajectories converge to these 4 data points. But there are, in this case, these diagonal lines that define the Voronoi boundaries between the cells associated with these 4 points. And trajectories that are initialized on these boundaries will move along these boundaries and not collapse back to the data. In particular, this example is actually quite interesting because numerically what happens is if you initialize, say, at a point along this line here, one will move along this line, and at some point, the weights associated with these two faraway data points, not only do they approach zero, but they actually numerically go to zero. And so the limit point then of the dynamics ends up just being at the mean of these two data points, which is really all that the ODE at some point will really see, because numerically, these points will just no longer exist because their weights will be exactly zero. And lastly, this collapse is onto the training data points is also something that's observed with images, and something that we can see by setting up examples with very limited training sets. So what we considered was a problem where we had two images consisting of the two plots that we have here on the left, where each image consisted of a single yellow square embedded within this empty background at either the top left of the image or at the bottom right of the image. And what we looked at what were the generated images from these models as we trained a score network. In particular, here we used one of the popular score networks in this developed as part of this work on elucidating the design space of these score-based diffusion models. And on the right, we're going to plot the generated samples, in particular 16 of those samples, after a certain number of epochs of training the network. So initially, we observe after 2,000 epochs, samples that are very grainy and don't really represent the original data. But as we iterate this, we start to get some crisper images. But at the initial times of training, what we are generated are actually samples which one can claim are new samples that, and interestingly, it might have learned some properties of the data distribution by generating, for instance, a sample that was consisted of an image like the one here that I'm highlighting that had a square that was nowhere where the original squares were in the two training data points. But as we continue iterating this process, eventually after, for instance, in this case, about 50,000 epochs, all of the generated samples are just the two samples that we had in the training data set, consisting of squares at either the top left or the bottom right. And so, and this is, in a sense, not too surprising because of the fact that we know that it's converging to this empirical Gaussian mixture score. But overall, this then motivates the next part of our work, which is the fact that it's necessary to regularize these methods to avoid recovering this empirical score. And in fact, there's many ways to do that. One of them that we're seeing is through just the early stopping of these networks in training, but also the use, for instance, of limited parameterizations for these score networks that avoid recovering these empirical Gaussian mixture score. So lastly, just to conclude, so what we showed in this work is that when working with this empirical score function, the dynamics associated with the reverse process have some interesting behavior where we can say that the limiting points of the dynamics contain both the training data, but also can lie along boundaries of these Voronoi cells that are defined based on the training data. And moreover, when we are approaching one of the data points in the transform dynamics, we converge exponentially fast to one of the data points. As part of our future work, we're looking at how these certain regularization methods behave, in particular when we incorporate, look at the dynamics associated with regularized score functions. So with that, I'd like to thank you for your attention and happy to take any questions.
Yes, thank you so much. Any questions?
Thank you for the great talk. There is something I don't really understand. So you use the empirical score function for an empirical distribution, which is actually the perfect score. All right, so the objective function is 0. So if you have enough noise in the forward process such that the terminal distribution is approximately the Gaussian or, the prior distribution, and then by starting from this distribution, you're supposed to get back to the true distribution, so to collapse. So I don't really understand in which cases you can reach the Voronoi cell boundaries, because if you add enough noise, you're supposed to collapse to get back to the original points. You understand what I mean, or?
I do.
Yeah.
Thanks for the question. So, one thing that we haven't ruled out is that what we're saying is that there potentially one of the limit points of those ODEs consisted of points along these Voronoi boundaries, but we didn't say whether that is, for instance, a likely event to occur. And that depends a lot on exactly what is the probability for the initial condition. So that is something to be worked out, whether this is, for instance, a measure 0 event.
Yeah.
Yeah, to that, I think, if you look from the SDE perspective, it's clear. Like the Voronoi boundaries are only an artifact of the ODE, right? In the SDE, you would not get them because you will for sure leave them. And if you also look from it from a forward perspective, then it's just clear that, with probability 0, you will land on these boundaries in between, right? So, and also with the, so did I understand it right that you're saying that you will always be exponentially close to a data point in a small time interval?
So what we said is once after a sufficient amount of time, then we will converge exponentially fast to one of the data points.
When there's no upper bound anymore, depending on the initial condition of that. Because if you think again, just from a forward perspective, then at each time epsilon, because you're adding Gaussian noise, you can be as far away as you want from the data points, right? You will have a strong inward pull again, but you can't say that you will be in a very small ball. This is what I don't understand.
So are you asking exactly what is this that is critical time? So that you are within this close neighborhood?
Yeah, maybe that, yeah.
Yeah, so this will depend, and how it depends on like the forward process. Yeah, so it does depend on, it will scale with the, there's an explicit expression in terms of the data as well as how big the initial time, like how much variance you add in the forward process. So that it will depend on the initial process, and based on that, you can work out how much time that is going to be, and if you evolve far away from the data, will take potentially a longer time to get back to the bulk and to hit that critical time. But once you get past it, then you get this rate, which doesn't depend anymore on the initial condition.
But the critical time depends on the initial condition.
Correct, yes.
Okay, yeah. Yeah, what I was just, because if you think like, you know exactly at each time where all the mass is, right? If you think about the forward process, so you can exactly say with probability this, I will be so close to the data points and whatever. And there's always a probability to be infinitely far because we're adding Gaussian noise. This is what confused me.
I see, yes. Yes, yeah, I see what you're saying. I'm happy to show the expression.
We'll have time for one more question, Ricardo.
Thank you for the great talk. Is there a similar analysis for the reverse SDE, not reverse ODE?
Thank you very much. So we only looked at the ODE, but presumably one can also look at the SD as well. Yeah, it was just from we were interested in kind of working out these explicit limit points of the ODE and the rates, but so we did not look yet at the SDE, but one can.
But this is no issue with the microphones. So maybe you have to raise your voice. Is there any last question? Okay, maybe, yeah, quick one, but please raise your voice. That means.
Have you guys thought at all about the role of that discretization error plays in regularizing? So if you take like very large step sizes, for instance, in your final image experiment.
Yes, great question. So thank you. So one thing that that we've also observed is that because there's these different regimes of the ODE, regions where the ODE behaves like it's moving just towards the data, and then regions where it's collapsing back onto the data. Then if you can separate out these regions, then for instance, in some of the initial regions where you're just moving towards the data, then you can take very large steps and without committing a huge error. So there is all of our analysis here doesn't account for the discretization error, but potentially one can use the behavior to come up with schemes for discretizing the ODE.
Okay, excellent.
Thank you very much.
So much. Okay, that's the